Good morning and thanks for all for coming here. I'm going to talk on using DTrace for GNOME performance analysis. So GNOME is being the default desktop shipped with OpenSolaris and various Linux distros. So it makes sense to understand how GNOME is performing in various platforms. So why is it interesting for OpenSolaris developers is that DTrace offers us a very good platform to probe into software without much overhead in using the software itself. So I have actually made a prototype which has USDT probes into it. So there are ways of using PID provider also to get statistics from DTrace, but USDT probes give us more information. So let's take a look at what I've done. So this is the agenda I have for today. The DTrace intro part was for, if at all anyone didn't know about DTrace, I can give a quick intro, not really a complete one. So I'm just taking a poll. Do anyone want that DTrace intro, or I can skip that? Good. I have some embarrassing slides there. Yeah, I skip all these. Yeah. So this is the problem statement I've taken to work on for this talk. So we need to collect performance metrics of GNOME applications in a non-intrusive manner. Here is where OpenSolaris and DTrace comes to help. So traditionally, the way you collect information on performance or anything on a software is through printf statements or debug statements. So how we do this is we have it hashdeft so that we can have a debug binary where we can collect information and then understand performance, make some tweaks, then remove all the debug statements, send the binary to the customer, and okay. So this is this is intrusive, as in the binary. Your printf statements can affect performance of the binary, and it's not exactly the same as what the customer or the user is going to use. So you're really not sure what performance you measured is the same as what the others are seeing. Second one is in Linux, there's something called system tab. You must have heard of it. So it is like DTrace. Not sure how like DTrace it is. So this is information I've got from the GNOME performance page. So there are a couple of scripts which use the system call provider equivalent in system tab to collect information on what are the system calls GNOME applications in Linux use. They have a script which calculates login time and all the system calls being done during the login process. So this information saying that ustack kind of an implementation in system tab is only available for you have to recompile the kernel and stuff. So any mistake in whatever I'm saying is because of the person who edited the wiki in GNOME performance page. Yeah, it lacks probe specific to apps. So this, by probe specific to apps, I mean I did not see any methods mentioned to add probes to your application so that which you can use later. Okay, so what DTrace can offer? So DTrace has something called the PID provider, which is their default in. So without any code modification, you can gather statistics of your application. So there's another thing called USDT probes, which all of us know. This is very helpful in exposing application-specific information. Like you can add instrumentation points within your application, which will give information like some local variables which might be of interest. Or you can also detect code flow saying that, okay, this if condition is taken and stuff like that. It's totally left to the imagination of the application developer and driven by use. Yeah, the important part is it can be present in production and it has zero disabled probe effect. I'm not going to explain why it is zero probe effect when it's disabled. So for this information, we can read the Usenix paper and convince ourselves that there is very minimal effect. Okay, so this is an introduction to what the PID provider is capable of. So you can basically instrument any instruction in an application. Again, it has no probe effect like I already said. And when the probes are enabled, there is a small overhead, and that's restricted to the process we are tracing. So you pay the price of performance to understand the behavior of the software. So that's okay, I guess. Okay, this is one example where I've traced the Nautilus file manager in GNOME. And this is a particular function which gets triggered when a file is being read. This happens when the Nautilus gets all the thumbnails of every files in the folders. So that gets triggered. So quite a few of them. Okay, so the limitation of PID provider, when you want to specifically look into the application performance, in this instance the GNOME, retrieving, so GNOME has this object system where the information is not available outside as primitive data types like int, string, and char. So there are some indirections which we have to traverse to get to the actual content which we are interested in. So getting that through PID provider is non-trivial. So you might have to copy in structures and then, copy in, so you'll get pointers, so you'll have to copy in that particular offset of that. So it's not very straightforward, not very usable. And tracing places other than entry of a function and exit of a function is again difficult. You'll have to understand the disassembly and get into the correct offset of where you want to exactly go into your code. So this is again what USDT probes can do. So I guess I'll skip this. If anyone wants to know anything, I'll stop. This is a simple hello world in case you want to know. So these are basically exactly the same steps we have to follow to add the probes into your application. It gets slightly complicated if you have some huge make files to add these lines into. So you have to be careful at what stage you add the DTrace line there, and so that depends on the application you're tracing. Yeah, so there are already some real world software which use USDT probes to get information out of their application. So one of the example is Apache. So they have these set of high level probes which give information like the server has received request and it's processing request and so on and so forth. So that gives understanding for the developer, so what's exactly happening at this point of time. MySQL is another example. I'm not going to get into the details of this. So this is just to show that there are other real world software which have USDT probes enabled and are running without any issues and are more useful to understand the working. Okay, so where are the probes in the prototype I've just developed? They are placed in the core GNOME libs. So how GNOME works is, so this is a partial view of how GNOME looks. So the GTK application is basically all the applications you see in GNOME. Nautilus is a GTK application. That's the file manager. So everybody sits over there. So they all use the libraries present. glib is a core GNOME library. Gobject is the object library which GNOME heavily uses. GIO is for the IO abstraction. So the probes are placed in glib, GIO, and GTK. So in glib, I have so in glib I've added probes in the malloc equivalence. So this function called gmalloc, which all GNOME applications make calls in case they need memory. So gfree is the equivalent. gslicealloc is the slab allocator implementation present in glib. So applications which have requests of certain object sizes, so they create their own caches and they make allocations. So this is the probe matrix. So the function trace probe name is present here. The function traced is also described. So arg0 and arg1 are the data which is exposed by the probes. Okay. So this is one script I wrote to get some useful data from this probes I've added. So what this script exactly does is tries to compute the average lifetime of any address that was allocated using gmalloc and freed using gfree. So the first probe uses the PID provider to get the address of the memory we have allocated. So I don't need to explain the script, right? Yeah, so this is how the output looks. So Yeah, this is during the time the script ran for. Yeah, this is another script which calculates the distribution of sizes of the objects allocated. So this is again plain one-liner just for description. It's in a script. So this is the output which I've got. There's a very interesting thing here. There have been the largest requests have been for zero size mallocs, zero size G mallocs. So I've really not figured why that's happening. I didn't have the time. But on seeing the stack, user stack there, it looks like the application is trying to draw icons. So here Nautilus is trying to refresh its image, that folder image showing all the icons there. So this has been the common stack in all of the zero requests. So these kind of interesting information can be found very easily using probes like this. Yeah, probes in GTK. GTK is the GIMP toolkit. So this is used to draw the widgets you see on GNOME. This is one particular widget which often has taken a lot of time and people lost patience on this. This is the file chooser dialog which you see when So in your text editor, for example, so this now has opened pretty fast since there's no network mounted home or something. So traditionally this has been having unacceptable behavior, but it's gotten improved over time. So this was one of the complaints the GNOME performance page had. Yeah. Yeah. So the GNOME performance page, which is not really updated, had this problem saying that GTK file chooser dialog takes more time than that's acceptable. So I just added two probes on the entry and exit of the object initialization to just find out what time it takes to initialize the object. You can do various other things like what time it takes to update the widget and stuff like that. So this is just like to understand what we can get out of DTrace. Yeah, this is another script which just computes the time taken and just averages the time spent. Yeah, so this is the output for that. So we can add more probes into different portions of the widget creation, widget drawing and stuff for various other widgets as well. So and collect information on whether it's running in acceptable time limits or so. So this is the GIO library of GNOME. So this actually abstracts the IO operations in GNOME. So all applications which have any IO requests go through this library. Okay, there is GNOME VFS, which is also an old library which most of the applications have dropped using. The probes here, like it's mentioned, it's in the yeah. So I'll get back to the diagram for GIO to give some introduction. Yeah. So GIO separates different file backends. So the local file implementation, local file access, input-output access is present in libgio itself. The other file backends like FTP, WebDAV, and HTTP, which can be viewed by Nautilus also, has something called the GVFS backend. So that's how the calls go through. Yeah. So I think this matrix is fairly explanatory. So here there's some small information missing. So in this probe, I've also exposed the file name, so which is present in an object called gfile. So gfile has another offset, a member which says the file name of this thing. In the PIT provider, we cannot very straightforwardly get the file name from this, since you will have to copy in the gfile structure and then get into the offset. So here it will be, yeah. So this is for the FTP backend. So it's equivalent to the local file thing. Yeah. So they help in measuring the time spent in the read function and this thing. So yeah. So through this, just the arg0 gives you the file name here. So this is when Nautilus tries to read all the thumbnail information printed for you. Yeah, so the file name is got from the gfile object. Yeah. So these are the code changes I've made. They're not very big. So I guess the slides I think will be available in the site. So yeah. So what do I aim to do after this is get more probes into GNOME and probably ship OpenSolaris GNOME desktop with DTrace probes enabled by default like Firefox does. And next what we could do is get the dbus, if that stays for long, get that also DTrace enabled. So GNOME heavily uses dbus as of now. So if that stays, we can add more probes there. So that's all I have.